The part two of approximating the area underneath the curve, we're going to really dive in now. We're going to talk about using the definite integral to figure this out. And so as I've done in the past, we're going to kind of talk about what I'm trying to figure out and then do the actual problem. So right now I'm just trying to find the area under this curve. And you notice I'm bounded by the x-axis, and we'll talk about when that's not the case here, in our next section. But we'll notice that, so what I'm asking you to do is to find the area of this space right here, so this enclosed space. Now again, I'll reiterate the idea that in geometry we don't have a specific formula for this 3x squared plus 1 from -2 to 2. There's no book or anything. So what we're going to use is calculus, or integrals, or the definite integral. Okay, so let me just reprove my point again that we talked about in the last section, which is if I wanted to, I could put in some rectangles. So you'll notice if I put in some rectangles, let's say left bound, you'll notice that with the curved line or the x squared function or the parabola, you'll notice that the areas get a little bit goofy. If I have the right bound, you'll notice that I would definitely be, off from the area. And of course, you would say, well, let's just plug more rectangles in there. So for example, if I wanted to plug 100 rectangles in there, I know we did this in the last section. I just want to reiterate this idea of this infinitely many rectangles in the space provided. So you'll notice if I put 100 rectangles in the space, if I added up all those rectangles, I might get closer to the area, but not maybe exact. So then what about if I put in 500 rectangles? Let's just change that to 500. You'll notice that it's even more rectangles, but you can see that I'm still just a little off, okay? So again, that's where this formula comes from, this idea right here, which is the idea of putting in infinitely many rectangles into the space, adding up all those rectangles and getting my area under the curve. Now you'll notice that this is the same as this, which is the definite integral. This sign should look familiar. That's a summation sign, which is why it looks like an S. It's not the summation sign, I apologize. It's an integral sign, but it looks like an S because of the idea it comes from the summation. All right, so we're going to do this problem right here. I'm going to incorporate this idea and do a definite integral. Okay, I'm also going to show the other part, the fundamental theorem of calculus, to add to the end of this. All right, so here we go. Let's dive in. So we are going to write the problem. This A to B emphasizes the boundaries we're talking about. So we're talking from -2 to 2. Okay, so the lower bound goes on the bottom. So -2 to 2. All right, so let me emphasize that. This is the lower bound, okay, the lesser number bounded, and that'll show up in your interval it's talking about. Sometimes it'll just be in the problem if you're finding a definite integral just flat out, all right? But if we're talking about finding specifically an area, it would go from -2 to 2, and then you'd write the lower one there and the upper one here, okay? So then we're going to use our tricks we learned from our last two sections, which is finding the integral of this. Hold on, I'm getting ahead of myself. Let me write this in here. X squared plus 1 dx. The process is very similar to find the indefinite integral. We're only going to take another step past the indefinite integral. So let me write this out. Let's find the integral of 3x squared plus 1. So that would be 3x to the third over 3. Remember, we add 1 to the exponent, divide by that exponent, and then in this case it would be plus x, because we'd have x is 0, x to the 1 divided by 1, and we get x. Now in this case, unlike the indefinite integral, we would not put plus c because we are finding a definite integral. That definite integral idea comes from the part that we have -2 to 2, or we have numbers in this case. If we didn't have the numbers, we would then be back on the process of indefinite integrals. Okay. Now, once we have taken the integral of the function, what we're going to do is just emphasize the idea that we are finding the indefinite integral. We're just going to put this kind of larger line. It's not an absolute value line. It's just a straight line, and we just rewrite those bounds right here. So you might see this in your textbook, emphasizing the idea that I've taken the integral, and now I just need to do the next part, which is the definite integral. Okay. So I've got the integral here. I'm gonna kind of rewrite this just to simplify it. So I have x to the third, 3 divided by 3 plus x, and again that's bounded by this idea. I'm gonna rewrite this just a little bit. Let me put it a little bit more down here. So we have x to the third plus x, and again, that's bounded by, or I still have to find the definite integral here. Okay, so the next part of this is the fundamental theorem of calculus. So what we're going to say is this equals, when we find the definite integral, we are going to plug in the upper bound minus the lower bound into the integral, okay? And that's going to give us our answer. So this capital F emphasizes the idea that this is the capital F, this is the integral of f of x. The capital F emphasizes that. So now what I'm going to do is I'm just going to plug these numbers in to my integral, okay? So let me draw my little arrow here, emphasizing the idea of taking next step. So now we have, I'll draw the, now what I like to do personally is I like to draw these brackets, emphasizing this is the first part. And here, I'm going to put this in here. So let's see, plus x. All right, so I'm going to put the 2 in here. That is the first bound, the upper bound. So this is the first part here, is the blue. And again, I put that in brackets because I find that if I do that, it helps me kind of work through my, if I did make a mistake, I can go back through and kind of see where I might have made that mistake, okay? And then we have the subtraction sign, which is right here, all right? Then I'm going to do another bracket. And I'm going to do the exact same thing I did there, except of course, instead of having positive 2 in there, I'm going to be putting in negative 2. All right. Okay, so again, that negative 2 is this part. So this is the f of a, and this is the f of b. Okay, so I just drew those lines over there. And now all I got to do is just run a basic operation. So we get, let's see, 8 plus 2. I'll draw everything out for you here. Minus, in this case, this would be negative 8, because negative 2 to the third is negative 2 times negative 2 times negative 2, plus the negative 2. Trust me, I've been in situations where I've worked these problems all the way through and I missed a negative sign. So be aware, don't rush yourself. And then we have 10 minus, and you'll notice this comes out to negative 10, which comes out to be 20. And you're probably asking yourself, wow, that's kind of a convenient number for the area underneath the curve. But that is the answer, right? Parabolas, when you get into like radicals and rational functions, it might come out more as a decimal. Or in the case with this one, I picked a nice integral to do because I didn't feel like dealing with fractions. So in this case, I picked a nice function to deal with. But the answer, nonetheless, is 20. Okay? So a lot of people like this instead of the indefinite integrals because it allows you to get a finite answer, which in the last couple sections we've just been finding an additional function, or the indefinite integral. So this is, we're going to talk about how maybe when we do substitution or maybe some unique functions here in the next couple of videos, but please understand that all we're doing is we're taking the indefinite integral and we're just plugging in numbers into it, both the upper one, f of b, minus f of a, and then we put them together and we get our answer. Okay, make sure, I know I'm talking a little long here, make sure that you don't forget this is a negative sign. And that's again why I create those brackets, because that tells me I need to distribute that to the next number. Okay, obviously our area couldn't be 0. So if I came back and I did this problem and I was like, oh, my answer was 0, obviously the answer is not 0 based upon this graphic right here. It's got to be some sort of area. Okay, so thank you very much for listening, and please watch other videos for help.